All right, today we're going to be talking about advanced osmosis biology, students. Let's jump in. So before we go too deeply into advanced osmosis, let's get some vocab underway. So a solvent is the liquid, usually water, that's going to dissolve something. And a solute is whatever substance that's in it. So for instance, Kool-Aid, which is usually in powder form, like most solutes originally are, is going to get dissolved in water, and then we get Kool-Aid. Other very common solutes are sugar and salt. Okay, so we're going to use these words, and when we combine those things, we get a solution. When we have a lot of Kool-Aid, we would have a high concentration. Remember, concentration is the number of something, specifically solute particles, now we can say, in a specific area or volume of a liquid. So higher concentration, more Kool-Aid particles in the water, probably darker red. So we would look at this and we would see the orange is labeled as a solute. Where is there a higher concentration, the right or the left? There's a higher concentration of solute particles on the right. But where is there more water? There's more water on the left. So because there's an uneven amount of these things, they're going to move around until they get to equilibrium. Okay? So we're going to be talking about concentration a lot, so I'm going to really recommend you abbreviate concentration as C-O-N-C, because you're going to just get tired of writing it out. As we go through these notes, we're going to think about three major types of situations, and we're going to have names for these situations, and these are all going to be about how and where water is going to move, whether it's into the cell, out of the cell, or it's going to be both. Okay, and we call these words the following weird words. They are hypotonic, hypertonic, and isotonic. Okay, try saying them. Hypotonic, hypertonic, and isotonic. Very weird, but they all end in tonic, so to save ourselves a little bit in the notes, we're probably going to abbreviate them by the part that's different, just the beginning. Hypo, hyper, iso. Okay, and all of these things are comparing the amount of solutes inside and outside the cell. And that's going to be what allows us to predict the movement of water. Is the water going to go into the cell, out of the cell, or who knows, maybe a little bit of both. So again, I'm going to be abbreviating them a lot, and I highly recommend you do the same. It'll make your life way better. Okay, for hypo, okay, hypo. I like to call this the hippo one. So when water is in a hypotonic solution, the solution is going to look like this. Okay, the solute concentration is lower outside the cell than the solute concentration inside the cell. So if we look at this picture and we look at the percentages, they're going to tell us a lot. The amount of salt percent outside is 10%. The amount of salt inside is 20%. We need them to be even. We can almost equally write the amount of water. If there's 10% salt, what percent will be water? 90% outside the cell. If there's 20% inside of the cell, what percent water will be inside? 80%. But we need it to be even, okay? Here we have a very liquidy solution. It's not very salty out there. So what direction will water need to move to make it even? To me, it seems like there's too much salt on here and there's too much water out here. So which way will water move to make it even? Well, water will flow into the cell. Why? Because there's more water, a higher amount of water outside than inside. So we would write an H out here, higher amount outside, and an L here, and water always moves from high to low. So we draw the movement of water from outside to inside. What's this going to do to the cell size if water's going and rushing in? Well, if water's rushing in, it's going to swell the cell up. The cell's going to get bigger. Think about that girl from Willy Wonka who becomes a big blueberry. Get really big, right? Which is why I like to call this hypo-hippo. It makes the cell look big like a hippo. If it was an animal cell, the cell actually might burst because the cell membrane's not used to so much pressure. But what about a plant cell? What does a plant cell have on the outside that could help it? A plant cell has a structure that gives support on the outside, and we call that structure the cell wall. Okay, so a plant cell might burst, but an animal cell might burst, but a plant cell won't because it has the cell wall, which is pretty cool. Our next situation is isotonic, iso. This one we can immediately see from the picture. There's 10% salt on the outside and 10% salt on the inside. And if I look at the arrow, I can see the arrow is showing water going in and water going out. So I can automatically make some predictions about what this situation is like. This is where the concentration of solutes outside the cell, so the amount of salt outside, is equal to the amount of solutes inside, the amount of salt inside. So there's 10% salt on the outside and there's 10% salt on the inside. We've been calling this equal situation, what fancy word that sounds like equal? Equilibrium. So isotonic is just equilibrium, when the cell is at equilibrium with its solution it's sitting in. So what's the movement of water? Well, it's dynamic, meaning it's going to flow equally in and out, both ways. We call that dynamic equilibrium. Dynamic means there is movement. It's going to happen. It's changing, but it's existing. And what's going to happen to the cell size? Well, if there's equal amounts of water going in, then in equal amounts of water going out, is the cell really going to change size? No, the cell size will remain the same. So that's our second situation. Let's go on to the third situation. Hypertonic, which we call hyper. Hyper people tend to be what size? Small. That's going to help you remember. Okay, so this is a situation where the solution that the cell is put in has a higher concentration of solute, such as salt, on the outside, more salt on the outside than the amount of solute or salt on the inside. So I look at the picture, there is way more salt, 20% on the outside than the 10% on the inside. And I can already see, to balance it out, because it's so salty on the outside, the cell has water going out of the cell into the solution because it's just so salty on the outside. So what is the movement of water? Well, we can see from the picture that to balance it out, water is going from where there's a higher concentration of water, 90% water on the inside, to where there's a lower concentration of water on the outside, so that this becomes way less salty on the outside, so water will flow out. Because the cell is losing water really fast, what size will the cell get? The cell will shrink in size, and that is why I like to say hyper can help us remember that hyper people, they like to move around a lot, they burn off a lot of energy, and they tend to be smaller. So hyper reminds us that the cell should get smaller. Hyper people are smaller usually. Okay, so all these situations, we paid attention to how much water and how much salt was both inside and outside the cell. We can relate this to some labs that we're going to do and some real-life situations that we're going to do. So we'll practice this a lot in class, but I'm really impressed. Good job, guys.